All right. Hey, good morning. Today, guys, we're going to look at how to eyeball, just by eyeballing it, determine the type of reaction given a balanced chemical equation. All right. So, this is basically what we're going to look at today. So, in our previous discussion, guys, if you look at your notes previously, right, we talked about synthesis and decomposition. Again, when you eyeball this just by looking at it, guys, just by looking at it, how can you tell if a chemical reaction is synthesis? Well, again, if you divide the equation in half, right, on the arrow, right, and you see there's only one product, right, which means there's only one compound after the arrow, it has to be synthesis, all right? Okay, how do you know it's decomposition? Again, if you divide the equation into two, right, and if you only see one thing before the arrow, one compound before the arrow, that means you only have one reactant. That means there's this one is decomposition. So again, if you see there's only one compound, okay, one compound on one side, okay, just look at what side it's on. If it's after the arrow, that means you only have one product. That means that is synthesis. All right. If you look at the equation, you look at it, the compound is before the arrow. There's only one compound before the arrow. That has to be decomposition. All right. So what if you divide the equation? Okay, you divide the equation into two, and then you see there's actually two compounds. Okay, what if you divide the equation into two, like this one right here, right? Divide the equation into two, like this one right here, and you see there's two compounds after the arrow, but there's also two compounds before the arrow. So you have two compounds for reactants, two compounds for products. So what type of reaction is this? Well, that's where the other types go in. So look at it very closely first. If you see, okay, O2 as the reactant, so again, divided in half, right? If you see O2 as one of the reactants and CO2 and H2O as your products, this equation, this chemical equation must be a combustion reaction right there. So don't forget, there's two conditions here. It must have O2 as a reactant, okay? And it must have CO2 and H2O as products, all right? Now, wait a minute. What if you're looking at this, all right? You're looking at the chemical equation and you don't see the CO2. You don't see the CO2, right? You divide the equation into two. But let's say in the product side, you don't see the CO2, okay? Is that still combustion? No, it's not. If one of those three is missing or changed with something else, that's not combustion anymore, all right? So what if it's not CO2 and H2O after the arrow? Okay, after the arrow, you have something else. Before the arrow, there's no O2. So for example, this one right here. So let's look at this one on the left. So again, guys, if you look at this one right here, you divide it on the arrow, right? There's two compounds before, and then there's two compounds after. All right. Okay, same thing here. If you divide this on the arrow, there's two compounds before and two compounds after. Y'all see it? Okay. But there's no CO2, there's no H2O, and there's no O2. Okay, remember the O2 has to be before the arrow. CO2 and H2O has to be after the arrow for it to be combustion. So what do you call this? All right. So let's look at the reaction on the left. Okay. If you look closely, guys, at the left, if you divide this equation in half, you can clearly see that one of them is actually an element. And we discussed this before. So this is one is an element. Okay. All right. And how do I know again if it's an element? There's only one capital letter. So again, one capital letter. So one of the compounds only has one capital letter. Therefore, that has to be an element. Okay. Look at the other one. This one is not an element because look, there's more than one capital letter. So this one is a compound. Okay. All right. Let's look at the product side after the arrow. If you look closely, guys, after the arrow, you have here, this one has two capital letters, therefore this is a compound. But look at O2, it only has one capital letter, therefore this is an element. So what you have here, guys, is a chemical equation that has a compound and an element, okay, on both sides. Again, there's a compound and an element in both sides, okay? And if you look closely, guys, the element, if you look at the reactant side, that element, the F, actually replaces part of the compound. So it's like switching. So the element actually switches with one part of the compound. So look, the F replaces the O, forms your NaF. Okay, displaces the O. Okay, so what do you call this one right here? So this one is called a single replacement reaction. So again, how do you know it's single replacement? Again, if you have an element in a compound on each side of the chemical equation. Again, as long as you have an element in a compound on each side of the chemical equation, okay, that has to be a single replacement. All right. So, how about the other one? Look here. If you look closely at this one on the right, let's look at the equation on the right. Okay. If you look closely, this first one right here, the first reactant, is a compound. Again, how do I know? Again, count the capital letters. If you have more than one, it's a compound. Okay. How about this one right here? All right. Again, it has more than one capital letter. It's a compound. Okay. All right. Let's look at the product side. So again, NAF, compound. Okay. Because again, there's two capital letters there. BAO, this one is a compound. See it? So guys, if you look closely at this equation right here, and there are two compounds on each side, okay? This one is called a double replacement reaction. So again, double replacement. Why do you call it double replacement? Because if you look closely, guys, it seems like part of the compound switches with the other part of the other compound. So look here. If you look closely, the O here and the F here seems to switch. They're like switching partners. See it? So the Na now goes with the F and the Ba now goes with the O. So they're like switching partners, all right? So this one is like if you're in a ballroom, you're dancing with someone and another couple is dancing, it's like you're switching partners right here, okay? In single replacement, okay, it looks like there's a couple dancing right here, there's a couple right here, and then someone just cuts in, okay? Someone cuts in and dances with a girl. You see it? So that's the difference between single and double replacement. All right. Okay. Now, if you look closely, let's focus more on double replacement, guys. Double replacement, actually, there are a few special types of double replacement. Okay. All right. So there are actually a few more special types of double replacement. So, for example, look at this one right here. Okay. You should know just by eyeballing it that this one is a double replacement reaction. So, again, why? Because, again, this one is a compound, okay? This one is a compound. This one is a compound, and this one is a compound. So you have compounds on both sides, two compounds on both sides of the equation. All right. But what makes this a special type of double replacement is this. The reactants are actually two aqueous solutions. Okay. What do you mean by aqueous? Aqueous means in water. So these are solutions, all right? These are solutions in water. Okay. Okay, solutions. Okay, aqueous means solutions, all right? So you have here two aqueous reactants. Okay, they join together to form a solid. And this solid is your precipitate. Okay, and this is a special type. All right, and we're going to see this in one of our labs later on. So again, if you have two aqueous solutions, guys, forming a solid product, that has to be a precipitation reaction right there. Okay. All right, so don't forget that. So, is there another type? Yes, there is. All right, this one is called an acid base or neutralization reaction. All right, so guys, an acid base or neutralization reaction, guys, is a reaction between an acid and a base to form salt and water. All right, so how would you know if something is an acid? Well, the acid will start with the H. So the formula starts with an H. Got it? All right. How do you know if it's a base? The base, guys, ends in OH. Okay. Of course, there's going to be other acids. Okay. that don't really start with H, and other bases that don't end in OH. But for now, we're going to use that simple definition for our purpose of looking at acid-base reactions, right? And then if you look closely, guys, the H part of the acid joins with the OH part of the base to form your H2O, water. So H joins with the OH, right? And if you arrange those letters right there, you got H2O. So that forms your water. Okay. How about what's left behind? What's left behind, guys, forms your salt. Okay. And the salt is always the metal followed by the non-metal. So again, when you write this down, always write it down first metal followed by non-metal. All right. That's how you write down your salt. Okay. All right. So that's the special type right there, the acid base or neutralization reaction. Okay. So those are actually the types of reactions that we want to look at, right? But can we categorize them any further? Well, you can. Okay. In reality, guys, there is what you call redox or reduction oxidation reactions. All right. What is a redox reaction? A redox reaction, guys, involves a change in the oxidation number for two of the elements involved in the reaction. One element, the one that is oxidized, increases in oxidation number, while the other element decreases in oxidation number. Mr. Chu, I didn't get that. Don't worry, we'll discuss it further uh, when we go to the topic. But for now, we just need to make sure that when you eyeball this, you know it's a redox reaction. So how do you know that? Okay, well, it's very simple. Okay, the following are redox reactions: all synthesis, all decomposition, all combustion, on all single replacement reactions are redox reactions. All right. So what are not redox reactions? Well, double replacement is not redox. Precipitation is not redox, and acid base is not redox reaction. So, all right, don't forget that. Okay, Mr. Chua, I didn't get this. All right. So, how do you make this easier for me? How can I eyeball this, okay, and determine whether or not it's redox or not, and how can I determine the type of reaction? All right. Well, I made a flow chart for you just to be sure, since we're doing this like really quickly because of all the missed days. We're gonna do this really quickly. This is how you do it. All right. So look at this flow chart right here. Okay. Let's look at this flow chart right here. Okay. Oop. So look at the flow chart right here. Okay. So first of all, let's say you're given a certain reaction. Okay. The first thing you ask yourself, do you see only one product or one reactant? So you go down here, right? Ask yourself that. It's a flow chart. So if you say yes, all right. If you see only one product or one reactant, there's only two choices here. It's either this one is a synthesis or this is a decomposition. So ask yourself, where do you see that one thing? Is it one product? If it's a one product reaction, it has to be synthesis. Okay. If there's only one reactant, it has to be decomposition. Okay. All right. Let's say the answer was no. Okay. Ask yourself, do you see O2 as a reactant and H2O and CO2 as your products? If you say yes, it has to be combustion. If you say no, keep on going. Ask yourself, do you see two compounds on each side? If you say no, it has to be a single replacement reaction. All right. Okay. If you say yes, it's a double replacement. But what type? Okay. So ask yourself, do you see two aqueous reactants in a solid product? If you say yes, it has to be a precipitation reaction. Okay. If you say no, it has to be an acid base reaction. All right. So let's try it out. Let's try it out. Instead of me yapping all the way, let's just try it out. All right. Let's try it out. So for example, let's change, you see that orange box? Let's change it into an actual chemical reaction right there. See it? Okay. So the first thing you do is, again, divide the equation always in half, right on the arrow. Okay. All right. So let's see the first question. Do you see one product or one reactant? So let's look at it. Before the arrow, I see two things. Okay. After the arrow, I see two things. Therefore, my answer is no. So I have to go down here. Okay. All right. Ask yourself, do you see O2 as a reactant and H2O and CO2 as products? Well, I see CO2. Oh, well, I see H2O as a product, but I don't see any of the other two, which means the answer is still no. Okay, so keep on going. All right. Do you see two compounds on each side? Well, yes, we see two compounds, two things before the arrow, two things after the arrow. So, yes. Okay. Therefore, this thing is a double replacement. Okay. So, check. So, this one is a double replacement. All right. Okay. But is it a special type? So, let's see. Ask yourself, do you see two aqueous reactants in a solid product? Well, let's see. I don't see any of that little subscript that says AQ. I don't see those little subscripts that says S. Okay. So therefore, the answer is no. Therefore, this one is an acid-base reaction. Okay. So that's how you use this flowchart right here. Mr. Cho, what do you mean by AQ? All right. Aqueous reactants in a solid product. All right. Again, guys, when you do that, you have to look for this one right here. See it? See these AQ right here? AQ means aqueous. Okay. All right. This tells you the state of the compound during the reaction. S means a solid. All right. And if ever later on L is a liquid, okay, obviously G would be a gas. Okay. But we're not going to use these two anytime soon. All right. So that's basically what it is. Oh, by the way, if you look at our flow chart, guys, if you look at our flow chart, okay, how would you know which ones are redox and which ones are not redox? So, well, redox will be the ones in green. So, redox is green. Okay, don't forget. And anything that's not green is not redox, obviously. All right. So there you go. So synthesis, decomposition, combustion, and single replacement, they're all redox reactions. All right. So let's take another example. All right. Look at this one right here. Okay. Okay. So again, the first thing you always do is divide the equation in half. Okay. Now look at it. Ask yourself, do you see only one product or one reactant? No, because there's two things before the arrow, two things after. So the answer is no. I go this way. Okay. Do you see O2 as a reactant, H2O and CO2 as products? Again, I don't see any of those, so no. Okay. Ask yourself, do you see two compounds on each side? Yes. Okay. How do you know again if it's a compound? Look at the capital letters. All right. If you only see one capital letter, okay, if there's only one capital letter, that has to be an element. Okay. Don't forget. And since there's two capital letters on each one, okay, this has two, so this is a compound. This is a compound, compound, compound. Okay, I see two compounds on each side, so the answer is yes. Again, this has to be a double replacement. Okay, but what kind of double replacement? Is it a special type? So you keep on asking yourself, do you see two aqueous reactants in a solid product? So let's see. Oh, let me erase that. So do I see any aqueous? Okay, I see it. You see it? AQ, AQ before the arrow, and you must have the S. The most important thing there is the S. You must have two AQs before the arrow and an S after. All right. So therefore, the answer here is yes. So this is called a precipitation reaction. And which one is the precipitate? It's the solid. So this is your precipitate right there. Okay. That is called your precipitate. Okay. And that is the solid form. Okay. Precipitate. All right. Let's try it out one more time. Okay. How about this one right here? Let's try this one right here. How about if this is the one that we're looking at? Okay. All right. So look. Again, always start by dividing the equation in half. Okay. All right. Do you see only one product or one reactant? Yes. Before the arrow, there's only one thing. So the answer is yes. Okay. Where do you see that one thing? It's before the arrow, therefore it's a reactant. Therefore, this thing is decomposition. And if you look closely, this one is green, so this is also a redox reaction. All right. Let's try out if there's a, let's see if there's another example. Okay. All right. Look at this one right here. Okay. All right. Again, divided in half. Okay. Do you see only one product or one reactant? No. There's two things before, two things after. So the answer is no. Go down. Do you see O2 as a reactant? I see it right there. But do I see H2O and CO2 as products? No. Therefore, I keep on going down. Okay. All right. I keep on going down. Do you see two compounds on each side? Let's check. Is this a compound? Yes. Is this a compound? No. This is an element because there's only one capital letter. Is this a compound? Yes. Is this a compound? No. It's an element because, again, there's only one capital letter. Therefore, the answer here is no. Therefore, this one is a single replacement, and this is also a redox reaction. All right. So hopefully, when you look at the equations, go practice using this flowchart. Hopefully, this helps you out. And if you have any questions, go hit me up in the chat, and we'll look at other examples after this. All right. Very good.